In this video, I want to talk about why calculus was developed the way that it was. And the reason that I want to discuss this is because in a normal calculus course, things are presented like a mathematician would present them. So, in other words, you're given a bunch of definitions, a bunch of axioms that you're supposed to accept without evidence. And then, if the class is any good, they're supposed to basically use logical mathematical reasoning to prove various theorems. Now, this is good, and this is a good way to understand the rigor behind calculus, but it's not very good for understanding the intuition. It's not very good for understanding why the axioms were chosen in the ways that they were. So in this video, I want to try to give an idea of why that was. And this whole story starts with a guy by the name of Isaac Newton. So if you've never heard of Isaac Newton, I highly recommend that you look him up. He's probably one of the best mathematicians and physicists of all time. Um, Basically, he was trying to understand how gravity worked. In order to really do it rigorously with mathematics, he needed to invent calculus. So he basically invented calculus to solve the physics problems he was working on. So he basically invented several subfields in math and physics. So which is pretty impressive. Now I just want to mention that Gottfried Leibniz also he's credited with Leibniz. He's credited with being the co-developer of calculus. They both actually developed a different kind of calculus independently, which was fundamentally the same kind of ideas and different notations. But in this video, I'm just going to focus on Isaac Newton and basically how he came up with his ideas. So the first I want to talk about the basic problem that he was working on. So the problem was to understand why the planets moved the way that they did. So why do planets move how they do? That was what Isaac Newton was trying to understand. Um, there were there were several there were several pieces of knowledge that he had at the time based on the work of previous scientists. One of them was basically Kepler's laws. So, uh, what did he know? So, what did he know? What was his thought process? The first thing is as I mentioned before, Kepler's laws. So, there's actually three separate laws for Kepler's laws, but the long story short, planetary orbits are elliptical, is what Kepler's laws say. Planetary orbits are elliptical. So what that means is it was previously thought by, say, the ancient Greeks that the that the planetary orbits were actually circular. So if you think, and it was actually thought that the sun was at the Earth was at the center of the solar system. So if you imagine this as being, actually, let me make that a little bit bigger. Um, if we imagine the planet Earth here, the way that people previously imagined it was that all the planets going around the Earth, that's a bad circle, but just imagine that's a perfect circle. And then that's essentially what people saw when they looked up at the sky, um, with different planets being in different spots at the same time. Now, Kepler, what he said, first off, this was discovered before Kepler, that the sun was actually the center of the solar system. But beyond that, what he discovered is that the orbits of the planets are actually ellipses. So the orbits are actually more like this, is what Kepler said. So this was known at the time, and this was it was basically a series of very solid experimental observations over a long period of time. So just every time they looked up at the night sky for decades or even hundreds of years, they noticed that you could predict where various planets were based on this elliptical model. And Newton knew about this at the time. Now, what Newton's major insight was, which is it's pretty difficult to explain, so I'm not going to get into it because that's more appropriate for like an in-depth physics course. But basically, what Newton realized is if you pretend like there's an imaginary force, he sort of invented the word force. between these two objects. So like any objects with mass, they attract each other. So like let's say when we're here, when the planet's here in its orbit, it's being pulled inward directly towards the sun. And now when it's over here, now it's being pulled this way. And when it's over here, it's being pulled this way. So if you imagine an imaginary force holding the planet in its orbit, that can explain why the planet doesn't just go flying off into space. Because you might imagine, if you're going around in a circle, what's to stop you from just going flying off into space? And the answer that Newton had was basically that there's some force preventing that from happening, the force of gravity. Now, you might notice that the force can't be constant around this, around the path. So as the planet moves along the orbit, the force can't actually be constant. It has to change in some way. To be specific, when it gets a lot closer to the sun, if the force is as strong as it is here, then it would actually go flying off, or at least it would not follow the same elliptical path that it did last time. It would sort of veer off out into the open here, and maybe kind of make sort of like almost a flower petal looking path rather than a sort of a constant ellipse. In order for it to follow this approximate path, Newton discovered through a pretty ingenious but complicated set of reasoning that I don't want to get into, was that this force of gravity basically followed this equation. So the force of gravity between two objects with mass is equivalent to some constant. So he realized that they were just proportional, and in order to turn a proportionality equation, or in order to turn a proportionality into an equation, you need to substitute some constant in there. So there's some constant times m1, so like m1 would be the sun, for example, in this case, times m2, that would be like this planet, the planet that's orbiting around the sun, and then here we have r squared, where r is the distance between them. So for example, at this point in the path, r would be like this, and at this point in the path, r would be, from here to here, and at this point, r would be a lot smaller. So this is essentially the equation that Newton came up with to explain why planets orbited the way that they did. And now if you just think through the logic of this equation, just start to play around with it, you will notice a couple things. So if we double the mass, so let's say that, for example, the mass of the sun doubled, then that would mean the force of gravity has also doubled. It would mean basically planets are being pulled in with twice a force, and that would actually change the orbit of the planets. If the planet itself had double the mass, then that would basically double the force. And that would actually not change the orbit. I don't want to get into that right now, but that would change the force. It would not change the path, but it would change the force according to this equation. And if you, let's say, cut the distance in half. So for example, let's just say for the sake of argument, this path right here is actually half of this path right here. What that would mean is that the force here, the force of gravity here, is actually 4 times as strong. Because if you have two in the denominator, or you have 1/2 in the denominator, you can imagine it sort of like this. If you have 1/2 x in the denominator and you square that, you're going to end up with the 4 going on top and being left with the x squared on the bottom. So that's sort of how that would work. So this is the basic logic that Newton came up with, and it turns out that this was very solid. It explained the situation very well. For one, it explained why planets orbited in ellipses rather than perfect circles. In other words, if you just accept blindly that this equation is correct, at every point along the orbit, the planet is essentially feeling this force pulling it towards the center planet that it's orbiting around. If you just blindly accept that, blindly take it on faith, then you will actually get an elliptical orbit that is observed in reality. So, yeah, that's sort of a big deal. That's definitely progress. So that's the first thing, is basically Kepler's laws and basically explaining planetary motion with his force equation. His force is basically law of gravity. The second major insight that Newton had, and by the way, this can all be found in his book Principia Mathematica. It was published in I think the 1780s. or sorry, the 1680s, so hundreds of years ago, and it basically laid the foundation for modern physics and also modern calculus. It's a very big book, but that is sort of where the field itself started. So just thought I'd mention that. The second thing that he basically came up with is the idea of how forces affect motion. So how forces affect motion. Previously, the best view was from somebody named Aristotle, a Greek philosopher who's famous for a lot of other things. Basically, he said that the force that an object is exerted on an object is proportional to the mass of the object times the velocity of the object. So, for example, if you have an object, let's say you have one object and you're pushing it along, and you want to say, how hard do I have to push to move an object that's twice as massive as the first object? The answer would be, well, you have to push twice as hard. That sort of makes sense. That's logical. The part where this breaks down is that if you have a force of 0, let's say, that implies that the object stops moving. So, for example, if you go ice skating, let's say you're going ice skating. Here's a wall, and then you push off this wall. What's going to happen? Now, after you pushed off the wall, there's no force pushing you in this direction, but clearly you're going to be continue to go for a very long time. See, the reason that Aristotle thought this law made sense, and it actually sort of does make sense, is because of friction. So we live in a world full of frictional forces. If you actually take away the friction by maybe throwing something through the air, there's still a little bit of friction in the air, but it's obviously a lot less than on the ground. If you do that, or if you maybe go ice skating where the friction is very low on the ice, then things actually behave a lot more like Newton thought they behaved. And that was essentially what Newton realized. You can actually see that in the Principia. Newton actually explains. He basically makes a nuanced distinction here about how like air resistance would affect his laws and change them slightly. But if you actually go to outer space, according to Newton, you go out in space where you're away from all other planets and all other sources of gravity, then the law is actually this: F equals m times a, where a is or sorry a is basically change of velocity over change in time, in the same way that velocity is defined as change in distance over change in time. So, for example, a velocity you would measure in, say, miles per hour. An acceleration would be miles per hour per hour. So, in 1 hour, how much did your speed change? Whereas velocity is in 1 hour, how much did your total distance change, or how much distance did you cover? So anyway, with Newton's idea, if you this is actually Newton's second law, by the way. So second law, and then first law is actually a special case of the second law, the law of inertia. First law is when force equals 0. So if you imagine the force equals 0 here, so what does that mean? That means 0 equals 0. So ma equals 0. M is a constant. The mass of an object doesn't really change, so that means the acceleration is 0. So according to this equation, if you're not pushing on an object, then it's not accelerating. That's essentially what this equation says when the force is 0. And when that happens, so for example, if you're in space and you throw a baseball, and then you let go of the baseball as you throw it, this law says that it will not accelerate, it will not speed up, and it will not slow down forever until some other force acts on it. Basically, it will continue at the same speed as when it left your hand forever. So the velocity will stay constant. It still has a velocity. It's still traveling at a certain speed. Don't misunderstand this, and don't think that this means that its speed is 0. Its speed is whatever it was when you started. It's just that its speed is not changing. That's all this law says. So this was another one of Newton's major kind of innovations in his book, The Principia Mathematica. And if you think about it, thinking through these two relations, basically the force of gravity, the ability to calculate a force, and then basically equations to determine how an object moves based on a force acting on it. If you actually think about the combination of those two things, that actually gives you a procedure for finding out how fast certain objects will move based on which forces are on them. So, for example, the third major insight that Newton had, based on the connection of these ideas, was that the same law that causes gravity causes objects on Earth to fall to the ground. That was basically his third major insight. Causes planets to orbit, causes objects to fall towards Earth. So basically, Newton's view, he actually generalized his view a lot more. It wasn't merely that planets obey the law of gravity. For Newton, literally everything obeyed the law of gravity. So any two masses in the entire universe have an attractive force between one another. So it's just that usually we can't see that unless we're talking about very very massive objects. That's why it's not obvious. So with planets, those are gigantic and extremely massive. So yeah, of course we can see other planets orbiting one another. Whereas when you're standing next to some other person, you don't really feel a whole lot of force between the two of you. However, when you're talking about the situation where you're talking about the attractive force between a planet and an object, then you can also detect the results. So for example, if you think about yourself standing on the surface of the earth, so you're standing here, let me just draw a stick figure, and you have an object, let's say a baseball or an apple in your hand, and you let go of it, then basically it's just gonna fall down to the earth until it hits the ground, and then it's just gonna stay there, right? So one way to look at this is actually to um, is actually to imagine yourself. Imagine a gigantic Earth, and I'm gonna not this obviously won't be drawn to scale, but imagine the distance to the very center of the Earth. Imagine this is the whole Earth. What you can actually imagine. You can imagine this object here being attracted with the force of gravity towards the Earth, and the Earth is also attracted backwards. Now, if you apply Newton's law of gravity, what you'll find is that you can actually calculate how fast this object should accelerate or fall towards the ground. Now, one caveat that people usually do in a physics class is that they basically ignore the difference between this distance and this distance, because if you think about it technically, the force of gravity basically says that as your distance between the objects gets closer, the force of gravity increases. So the gravity is actually stronger touching the Earth than it is, say, 10 feet above the Earth or 10 meters above the Earth. But it's such a small difference that it doesn't really matter. So, for example, like the radius of the Earth, which would be the distance in this case, that would be the vast majority of the distance. I actually looked this up. It's on the order of magnitude of 6,371,000 meters. So 6,371 kilometers or 6,371,000 meters. That's how long this distance is. If you took an object up to the top of the Earth, so you say, and I'll call this distance here delta x, basically the distance that you drop it from, or I'll just call it distant. I'll just call it distance. How about that? That's probably better. So I'll just call this here the distance. Basically the distance from the ground to the height that you're holding the object. Let's say you did that 1,000 meters. So let's say d is 1 kilometer. You're holding it 1,000 meters above the ground, above the earth. What does that mean? That means you're really only the force of gravity between where you're holding it and when it hits the ground is only going to fluctuate 0.015%. So, way less than 1%. If you hold it, maybe say 1 meter in the air, which is a lot more common when you actually go to test it, then divide this number by 1,000. So 0.0000. We had 1 0 before, so now we need 3 more zeros, and then 1.5%. So, it's basically negligible. So that's why people actually assume that the gravity here between this point at the top of where you're dropping it and the bottom when it hits the ground is the same. Now, it's not literally the same, but for the purpose of accurate calculations, you can basically assume it's the same without getting the wrong answer. So if we actually calculate this force of gravity, so let's do that, and I'm going to use the actual numbers for, say, the planet Earth. The force of gravity equals, let's see, I actually looked these up. So the mass of the planet Earth is 5.9722 times 10 to the 24th. Sorry, let me write that a little bit better. It should be 10 to the 24th power. So that's the mass of the planet Earth. And then we have m, the mass of our object. I'm just going to keep that as m because that can vary. And actually, I should have multiplied this by a gravitational constant too. So let me do that. The gravitational constant here is 6.67 times 10 to the negative 11. So that's actually an extremely small number. That's the big G. So up in our equation previously, actually let me pull that equation down here, or at least rewrite it so that we can sort of see that. So yeah, let me just get rid of this. So remember, the equation that we're talking about is I'm just going to rewrite it real quick. The force of gravity is equal to some constant G, the constant of gravitation, times m1 times m2 divided by r squared. So this 6.67 times 10 to the negative 11th. So that's basically 10 zeros and then a 6. You can think of 0.0, 10 zeros and then a 6. So an extremely small number. That's the constant of gravitation here. This m1 is the mass of the Earth. This n here is mass 2, the mass of our object. And this r is actually the radius of the Earth. So basically how far away the object is from the very center of the Earth. The reason you care about the center of the Earth is because of a concept called basically the center of mass, or the center of gravity. I don't want to get into that in too much detail, but that's basically how the calculation is done in practice. And like I said before, that is 6,371,000 meters. And you square that. So if we're talking 6 million and change, we're going to be talking 36 trillion when we square that. So a gigantic number on the denominator. So we have a very large mass for the Earth, and we have a very small gravitational constant in the numerator and a very large radius in the denominator. And remember, this distance here, this covers from the center of the Earth to the surface. And then with the surface, you actually have the distance that you're holding the ball above the surface. But remember, we're ignoring that because it changes the answer by so little that we're just going to assume it's constant to make the calculation easier, basically. So this is basically how you calculate the force of gravity on an object that you're holding on the surface of the Earth. Now, if you go to another planet, for example, then all these numbers are going to change. This constant will stay the same, but the mass of the planet is going to be different, and the radius of the planet is going to be different. Just as an interesting side note, if you go to the moon and plug the specific numbers for the moon into this equation, you basically come out with 1/6 of the value for the Earth, which basically means your weight on the moon is 1/6 of what it is here. So you can think of that. That's why people can jump so much higher on the moon, and why it takes so much longer for them to fall after they jump. It's basically because the gravity, your weight on the moon is 1/6 of what it is here because of weaker gravity. So anyway, if you basically, now what you might notice is that on the Earth, most of this is a constant. So if you actually take these three numbers and multiply it together, what you'll get is what's called G. G is basically the acceleration due to gravity on Earth based on Earth specific numbers. And that's been experimentally determined. Well, actually, you can just plug it into this equation to get a very good answer to it, but it basically comes out to 9.81 meters per second. Meters per second squared. Sorry about that. Yeah, times the mass of the object that we're dropping. So this is actually sort of interesting because if you take this idea and run with it, what that actually implies is that no matter how massive different objects are, they all fall at the same rate. So, for example, if you have, because it actually, let me take this before I get there. Let me run with this. So this is how you actually calculate gravity on surface of Earth. Now, if you get really far away from the surface, this equation is going to cease to hold because remember that's basically the radius has changed. We're just assuming that the radius is so small, or that the distance above the Earth is so small that we can ignore that change, but it is actually there. So this only really holds close to the surface of the Earth. So this is how you calculate the force of gravity, basically the force acting on a ball, pulling it downward on the surface of the Earth. And what we know from Newton's equations of motion, so motion, because a force isn't good enough. If I tell you the force of this is whatever, then you might just say, well, who cares? What does that mean in practice? Well, what it means in practice is that if you add up all the forces, which is what this summation means, it means add up all the forces in the same directions acting on a particle or an object, and that's going to equal the mass times the acceleration. Now, let's assume in this example the only force acting on this ball is the force of gravity. There's actually going to be some air resistance too, but that's so minor that we can also ignore that for computations. So what I'm going to do is I'm going to take this F and set it equal to the force of gravity, since that's the only force acting on the object. So if I set MA equal to 9.81 meters per second squared times the mass of the object, well, what does this imply? We have M on this side and M on this side, so we can actually cross them out. What that tells you is that acceleration equals 9.81 meters per second squared on the surface of the Earth for any object. So in other words, just because, and the way to understand this is actually counterintuitive. This was first shown experimentally by Galileo I think it was the 1500s, but it was definitely counterintuitive. The way most people thought about it for most of human history was that, if you have an object that's twice as massive and you drop it, it's going to fall faster, obviously. Maybe not twice as fast, but at least faster. So if you have a bowling ball and, say, a baseball, well, obviously the bowling ball is going to fall faster. But it turns out that is not true. The only reason it looks true is, again, because of friction. That's another example of friction kind of confusing early physicists. If you eliminate friction entirely, so if you basically have a vacuum chamber where you suck all the air out of the chamber and you drop a bowling ball and you drop a feather, they'll actually fall at the same speed. They'll actually hit the ground at the same time. They'll accelerate at the same rate, and their speeds will be the same at each point in time. And that's actually, that holds for any object. No matter what mass you plug in here, the acceleration that you feel due to the force of gravity is independent of the mass. So this is basically what Newton was thinking at the time. This is all physics, by the way. I haven't said a single thing about calculus. I mean, I've done a little bit of algebra to actually use the equations that we've discussed in this video, but I haven't said a single thing about calculus yet. This is just setting the stage for that. So before I end this video, I want to just leave you with the problem that, this all leads into, and then in further videos, then we're really going to get into the kind of the logic of calculus and why Newton felt the need to develop calculus to explain his theories. So I'm just going to leave you with this question. So if acceleration is 9.81 meters per second squared, how fast does the object go? So like how fast does the object move at each point in time? And, or sorry, time, and how much distance has it covered? And it's not going to be constant either. That's the key insight. So that's part of what makes the problem hard. So if you think about this, this is what Newton wanted to understand. So basically, yeah, his theories of physics, basically the law of gravitation says that okay, look, if I drop a ball from some height and maybe say it's going to go through the, or actually let me redraw this. Let me redraw this a little differently. Um, Newton says let's imagine different snapshots of when you drop the object. So this is the first snapshot, second snapshot, third, and then eventually it comes, eventually gets to the last snapshot where it hits the ground. So we'll start off with height of h, where we hold the object, or at least we hold the center of the object, and then over time, obviously, it's going to fall. It's going to fall, and eventually it's going to hit the ground. And Newton's question is, well, is it possible at each point in time to actually tell exactly how high the object is? So that's, for example, how much distance does it cover? So Newton didn't just want to know how long it takes to hit the ground. Of course, he did want to do that. But he wanted to know, where is the ball at every single point in time between when we drop it and when it hits the ground? When, t equals 0 when we drop it, and, t equals, we'll call that time final, TF. Newton wanted to know, well, is it possible to determine where the ball is at every point in time? This problem is what motivated him to create calculus. And this is what we're going to talk about in subsequent videos. Thank you.